dire alla classe, cioè
No, quello non è un microfono.
Sì, questo è quello si chiama il direzionale, non so perché è puntato di qua, non ho idea.
Forse devono entrare prima, ragazzi.
Sì, può essere. Quindi dovrebbe puntare verso me, no?
Sì, però non so.
Ok. Ma i recording stanno funzionando bene?
Non c'è quello di ieri.
Com'è?
Quello di ieri manca.
Non l'ho scordato. Mandatemi un'email, a un certo punto me lo mandate. Adesso forse lo posso fare direttamente adesso, posso farlo direttamente ora. Allora, nel momento in cui facciamo così. Allora, forse posso farlo da qui. Gestisci registrazioni.
Si muove.
La sposto adesso, la carico, la carico ora. Sposto su virtuale 21-22, apply econometrics, sposto. Quindi caricata, ragazzi,
Grazie.
Prego. Carichiamo pure quest'altra invece. Ok. Ok, allora Java speak, let's check here if you get okay, Jabra, so everything should work here now as well. Okay, now you should be more or less able to see my screen.
Secondo è di creare una cartella che sarà la cartella con lei, quindi ci metti tutti e poi no, sì.
A microphone is open. Okay, I should have everything now. And last. Okay, so I think we can start. I start recording. Okay. So good afternoon. Welcome to our class of applied econometrics. And first, before I start, I want to ask if there are questions. There is a question on maybe later on. It's a private one.
No, it's I already written it in Italian. I don't want to.
Okay. Okay. So I go on. Are there questions also from the people at home before I go on? I sent you as I do on a regular basis. I will send you teaching material for today, just to facilitate, to help what we do. I need some. Okay. So, what are we doing today? This is our roadmap today. We have been working on, first of all, let me show you what we are doing. We are working here. Okay, this is what we are doing now. Where is it? I lost it. Program, sorry, where is the program? Let me open the program. Yeah. So we are working here, testing hypothesis in the linear regression model. And what we did yesterday was the theory for single coefficient test. Today, we are moving to the most general case. So after today, we can cover everything. So, sorry. What we do today, the roadmap will be, we'll say a few words on the magic of the F distribution. Of course, I'm joking. Then we'll develop the general test theory. We said that we can arrange linear restrictions on the beta coefficients of the regression model using this notation. For instance, example, imagine that we have 3 regressors. So the beta is beta intercept 1 and 2, okay? And imagine that for some reason, I need to test the restriction that the constant is equal to 0. And for some reason related to my theory, to my problem, I want to test that beta 1 minus beta 2 is equal to 1, okay? Or if you prefer, beta 1 is equal to 1 plus beta 2, for some reason. So we know that we can arrange this kind of linear restriction in this form here. So how do we arrange intercept constant equal to 0. You simply, we are considering two restrictions. So Q is equal to 2, which means that the capital R matrix has two rows. The first row will be select beta 0, so row times column equal to beta 0, and put it equal to 0. Okay. Second row, say, just select beta 1 minus beta 2. So I have 1 minus 1 and minus 1. So this linear combination gives you exactly the second restriction. This is a very general way of writing linear restriction which cover many, many cases. So I will say something about the F distribution. So we will come back. I will add. Yesterday we saw a very basic thing about, say, theory distribution. Today we are coming back on that, because when we deal with this very general form, we need the F distribution, the chi-square, and F distribution. That will be the distribution we're going to use. And also, when dealing with the general case, as we did yesterday for restriction on single coefficient, we'll distinguish between case 1, n small, sigma square, none. Very unreasonable, unrealistic case, but we need to cover it in order to understand case 2. Case 2 is when n is small, but we don't know sigma square epsilon, so we need to estimate it from the data. And finally, case 3, n is large, and sigma square is unknown. Okay? So this will be what we are doing today. But I want to give you also some empirical motivations. So let me, since we are still fresh, relatively fresh, did you have classes this morning? How many hours? 3. Which course?
Sustainable economics.
Sustainable economics. Okay. Okay. But we are relatively fresh, so I want to come back on the example we have been discussing yesterday. Do you remember yesterday we attempted to estimate model demand for gasoline consumption? Okay. And we had a model like this. I sent you, before coming here, I sent you an email where you have a Gretel script that does the job I'm doing here. So you don't have to worry to follow me, to strictly follow me, because you already have everything, okay? But just, you have to follow me and understand. You don't have to you don't need necessarily to replicate what I'm doing. You need to understand, okay? So the model was, yesterday model was this one. Just let me, we are modeling, say, the log of per capita gasoline consumption. We regress that on a constant. We regress on, we regress on per capita expenditure, okay? We regress, of course, on the price, on the log of price of gasoline, okay? And what else? I said, okay, it is reasonable to assume that, say, consumption, gasoline consumption can be affected by, in a given year from the gasoline consumption in the previous year. So I'm putting some autoregressive effect in this model, and we estimated this model, and we started thinking, okay, how do we evaluate? In a sense, I'm going to anticipate what we should do on our slide. I'm anticipating, say, empirically, but the point is, how do we evaluate whether the model, the estimated model, is good or not? Of course, one thing, first of all, we check whether the elasticities we have in mind, the estimated elasticity, are consistent with my theoretical view. Recall that correlation is not causation. For instance, in this case, in our example, if you compute correlation between consumption of gasoline and the price of gasoline, you will find positive. But in our demand equation, of course, you want the demand equation must be downward sloping, okay? So you expect a negative relationship between the two, okay? And we did it we discovered that once we included in our demand also say expenditure, blah, 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 okay? And we checked, one of the check was, okay, we estimated the model by OLS. OLS means homoscedasticity, but I give up in this model. I don't know if we have, we'll test homoscedasticity, okay? You will find the script test for that. But the very special in this setup where I have time series data, I'm very concerned in checking whether the error at time t is uncorrelated with the error at time t-1. So, which, I mean, if that is the case, the big sigma, as we know, the big sigma is diagonal. So yesterday I show you by looking at, after estimation, by looking at the correlogram of the residuals. The residuals are kind of empirical measure of the errors. We don't see the errors, but after this estimation, we see the residuals, and the residuals are kind of realization of the errors, okay? The errors are not observable, but we have the residuals. And by studying the correlogram of the residuals, yesterday we discovered that we have some correlation. That was not good news, because think about one model where you have, say, plus epsilon t at the end, the error 10. The error 10 should be something which is not explainable by anything else. It's just a noise. If you find that the error time t is correlated with error time t-1, it means that it's not properly an error term. We are omitting something in the model. That is the point. So, very quickly, I repeat very quickly what we did yesterday. We estimated this model. The estimate looked pretty good, okay, from the point of view of sign of the coefficients, magnitude, but by looking at the residual correlogram, let me just focus on the red bar, just to simplify. We realized that we have one problem, even if there is not a huge deviation from absence of autocorrelation. And you can see that also from the p-value of the Q-statistic test, which is, well, not very, very low relative to 5%. It is almost 4%. But we, at the 5% level, we reject the null of absence of autocorrelation at leg 1. Okay? So there is something that my error term are some is not pure noise. There is some signal inside my error term, and that means that I'm not capturing, the regression model is not capturing all properly the dynamic of gasoline consumption. So what can I do? I show you what I do now, okay? And then, given what, I mean, if we look at the estimation output I get, I will go to motivate why we need to test, for instance, joint restrictions on the parameters of the linear regression model. Let me do the following job now, okay? This is my, I modify the model like this, okay? What I do is, yes, I have one leg of gasoline, but I want to include in my model also the log of total expenditure of, say, income, not only at time t, but also at time t-1, previous income, and I do the same also for the price of gasoline, okay? So I have basically, my regression model, I've included, so gasoline at time t depends on gasoline time t-1, income at time t, income at time t-1, price of gasoline t, and price of gasoline at time t-1, okay? So I have 1, 2, 3, 4, 5, 6 regressors, k is equal to 6. So relative to the previous model, I have included, say, also one leg of total expenditure and one leg of price of gasoline, okay? Now, I click OK, I get the estimates, and look at here. It's very interesting to notice, you can notice from the T ratio column here, that actually also, well, also the price of gasoline at time t-1 and also expenditure at time t-1 are significant. How can I claim that? Let me assume that this is a large sample. Okay, as I told you, for statisticians, infinite becomes at 31. I have 34 observations, but that is not the argument. The argument is that we are covering quite long span of data from 1960 until 1995. We can assume that we have we are dealing with a large sample. Okay, we are covering many years, so we have enough information to claim that capital T goes to infinity. So we know that in this case, if I want to investigate the significance of single coefficients, I have to compare the T ratio here with the critical values taken from the normal 0, 1, because we are in a large sample theory. Okay? Also the column of p-value here suggests that p-value are all smaller than 5%. So all coefficients are significant. So relative to the yesterday estimation, I was omitting two important regressors. I was omitting, say, this one and this one. Okay, but now let's look at the coefficients. Look here. Basically, I have the coefficient associated with gasoline at time t-1 is 1. So what I can do, I could bring this gasoline t-1 on the left-hand side of the equation. Imagine that this number is 1, just 1. I can shift that, the consumption t-1 on the right-hand side of the equation, and you understand that on the right-hand side of the equation, we have the growth rate of consumption. Is it strange what I'm saying? It's very, very simple, okay? So it's the growth rate. And look at the other, the very interesting thing from my point of view is that, look at this coefficient. I have 0.58, and with the lag, I have minus 0.52. It seems like they are kind of the same with different, with a change in the sign. And look at this. I have the elasticity of gasoline, the price of gasoline is minus 0.27, and price gasoline at t-1 is 0.23. So still I have the suspect that these two guys in the population could be the same, but with reversed sign. What I'm telling is this. I go to the slide I sent you this morning. I'm very tempted because, so the situation is, imagine that I have a model like this. I have, say, on the left-hand side, I have included the growth rate of consumption. Why I do that? Because this is 1. So it is very natural that I bring this one on the left-hand side, and I get growth rate of consumption here. Where is it? Here. Then, okay, I have a constant. Then look at here. Imagine that I have, say, beta 2 yt minus beta 2 yt minus 1. So this is beta 3. So imagine that beta 3 is equal to minus beta 2. And imagine that beta 5 is equal to minus beta 4. The model I'm dealing with, this model, actually is this one. It's a model in growth rate of the variables. So it is very tempting, from a point of view, to test that the beta 2 plus beta 3 is equal to 0. That means that I can rewrite the model like the in growth rate. And it is very tempting to test that beta 4 plus beta 5 is equal to 0, which means that I can rewrite the model also in first differences. So I'm moving from this equation here to this one. If these restrictions are supported by the data. And how can I write in the general form capital R beta equal to small r? Can I arrange this restriction in the general, very general form? Of course, the answer is yes. How many restrictions do I have here? I have 2 restrictions, 1 and 2. Okay. How do I manage the first restriction? I need that the sum of beta 2 plus beta 3 is equal to 0. So I have the first row of the capital R matrix will be 0, 1, 1. So I'm selecting the sum of these 2 guys, and I put it equal to 0. What about the second row? The second row, I have to select, say, beta 4 and beta 5. I have to sum these 2 guys and put equal to 0. So the second row will be something like this, 0. So it's in this estimate, in the estimated model, this one, the one I'm showing you, I'm very tempted to do the following job. First of all, I want to re-estimate this model in growth rates of consumption, because I want to move this guy on the left-hand side of the question. And if I do that, on the left-hand side of the question, I have log consumption T minus log consumption T minus 1, which is by definition the growth rate of a variable. When you have a variable in log and you take the first difference, please believe me, that is the growth rate. But if you don't believe me, which is you don't have, in principle, you should check everything I say. You just take your paper and your pen, and you know the property of logarithms, and check that if you have log okay, if I have log of xt, if I compute this guy minus log x t minus 1, the previous period, you know from the properties of logarithm that this is the log of the ratio of xt over xt minus 1. Now, I hate this stuff. I really don't like it. Now, very simple argument. Let me play a little bit with numerator. Okay, denominator is this guy. I write numerator like this. You should agree with me that I'm not doing magic also in this case. I write like this. You see, as you can realize, when I write my papers, I don't use Word. Please don't use Word. So I can do the following very simple trick. Okay, I don't know how to do. So I have done a very simple, let me put parentheses here. Okay, what I have done, I had xt, I added xt minus 1, and I subtracted xt minus 1. You should agree that this is, at the end of the day, is the log of, again, let me copy. So, I don't know why I'm wasting time with this stuff. I'm doing that for you. I'm doing that for you. But if you don't need, please let me know, okay? So you should agree that this is something like the first difference of xt, xt, put a parenthesis here, okay? Are you agree, do you agree up to this point? You should agree on that. Now, you should also agree that I can rewrite this like, say, 1 plus the growth rate of xt, the change, not the growth rate, the change of xt over xt minus 1. And let me notice that let me put a big parenthesis here, okay? I can write it like this. Parenthesis. You should agree that now the guy I'm selecting, what is this guy? This is the change over value at time t minus 1. That is when we use our computer, when we make what is the percentage change of a variable, that is the number. Do you agree on that? That is the growth rate of the variable. And so you also know from, if you have from calculus, you know that if you consider the Taylor, a first order Taylor expansion of log of 1 plus x, this is approximately, so let me say approx, what is equal? What is log of 1 plus x? What is the first term of a Taylor expansion, first order Taylor expansion? Have you ever heard about Taylor expansion? Yeah. So if x is a very small number here, what is log of 1 plus x? Is approximately x. Take your computer. If you imagine that you have, say, a rate of change of 3%, you can compute, say, 3% like this, or if you compute the log of 1 plus 0.03, you get 0.03. So, coming back to the point, when I take first difference, and this was the first difference of log xt, okay? Follow the reasoning I have done. The first difference of a logged variable, it's at the end of the day is equal to the growth rate of the variable. Okay, guys? So, now what I do, I re-estimate the model, I modify my model. Now I will put the dependent variable is the growth rate of gasoline. I get the same regressors as before, robust standard error, blah, blah, blah. And this is, now you can see the dependent variable is the first difference of gasoline, okay? And again, I have the same regressors as before. And what I want to do now, I want to test that, say, beta 2 plus beta 3 is equal to 0 in the population, which means that the two coefficients are the same with the reverted change, which means that the actual dependent variable is not the log of expenditure, but it will be the growth rate of income. And if I look at this coefficient, minus 0.27 and plus 0.23, I could argue it is very reasonable to assume that, say, in the population, the sum of beta 4 plus beta 5 could be equal to 0. So, if it is the case, if that null hypothesis is true, you should agree with me that the model I should take to the data is this one, the one in growth rates. But you should say, Professor, but did we solve the problem with this? Adding these legs, we find significant coefficient. Are we solving the problem, the correlogram of the residual term? Okay, let's give a look to it. So again, residual correlogram. Let me just show you now that look at the red bars now. The red bars are all inside the blue lines, the confidence bands. Look at the Q statistic, Q test. In all cases, at any possible lag, we don't observe any correlation. So basically, with this adding price of gasoline T-1 and adding expenditure T-1 among the regressors, it seems that I have captured all the signal or all the dynamics of per capita consumption, which means that the error term, as captured by the residuals, contains no signal because it is completely uncorrelated. This is good news. So, given that now the model looks very, very good, and let me show you also this graph. I mean, a ficted data plot. Look at it. It looks, I mean, I don't look at the R square. Yesterday, I show you that the R square can be anything. The R square makes sense only if you have, say, if you have to compare your model, if you have, say, a competing model, okay? So the nice thing about this model is that I capture, say, this, what is this? I capture quite well, this should be, this is related to the crisis of the end 79, end of 80s. This is of course, this is a drop in growth rate in consumption gasoline related to the oil shock of 79, as you can see. And also, what is, for instance, this drop here, the red line that we don't the model, the blue, does not seem to capture this peak here. What is this peak? 91.
It's the war in
yeah,
Iraq.
yeah. That is the Gulf War, the famous Gulf War. Yeah. So an increase of the price. If you look at the price now, you see a spike in the price, and of course you have a decline in gasoline consumption. But so it seems we capture very well these two peaks, this one and this one. Also this one, actually, this is 74. This is the first famous oil crisis worldwide. Now we complain about, say, the price of oil and the price of gasoline, which is really high, but this is not new. I remember my father sent me, well, in the 70s, the government said, don't go, please, Sunday, don't take your car, just go walking. We already have been experiencing oil crisis, and we'll experience, as long as we depend on oil stuff, will be all the time. You have crisis, we have crisis around the world, blah, blah, blah. We have a situation like that. That should be a nice argument toward moving toward green energy, blah, 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 blah. Okay, you know that much better than I know. Okay, but it's just a comment. Now, let me come back on my point. I don't want to, I like to talk about these things, but I have to focus on, I have to stick to the program, okay? Now, I want to test that this coefficient plus this is equal to 0, and this coefficient plus this is equal to 0, because if I accept the null, I can rewrite the model. I have a model in growth rates. I have growth rates on the left-hand side, and I have growth rates on the right-hand side. Is that clear, guys? Now, so I can rearrange in this way. I show you, this is a way of rearranging these two restrictions here. How do I do that? How can I do that in Gretel? Very quickly. It will be kind of, I'm going to upset you, but let's do together. No, where is the model? Is this? Yes, this one. So I go test linear restrictions. And now please recall that the first coefficient for Gretel is B1. the second will be B2. So I write B2 plus B3 equal to 0, comma. So it means that Q is not equal to 1 because I'm going to test another restriction. I have a second row in the big R matrix. Okay? So the next restriction, the second restriction will be B4 plus B5 equal to 0. If I accept that, I have a model in first differences. Otherwise, not. And since it will be otherwise, you will understand. We can understand what actually happens in this model after Professor Panagonitis' part. I think that he will be talking with you about at least the main ingredients about co-integration analysis, non-stationary variable. This is a model based on non-stationary variables. We are treating like stationary variables, but it's not important now for our purposes. So I click OK. And what I want to stress, what is the problem here? Okay, on my laptop, please believe me that he wanted the comma, but he doesn't want the comma here. Now, I get test statistic robust F, and this is now why today I'm talking with you about the F distribution, because Gretel is giving us an F2. Recall that Q is equal to 2. We have two restrictions, and I have an F of 10, 47 with a p-value. So what do we do about the null? Do we accept it or we reject it? Come on, guys.
Reject it.
We strongly reject it. We strongly reject it, unfortunately, and so my intuition was not correct. And in the bottom part, Gretel provides us with the estimated model under the restrictions. In this case, the restrictions are rejected by the data, not supported by the data. But if they were supported, I would get the following, restricted coefficient. In this case, you see that under the constraint, the sum of these two guys is equal to 0, and under the constraint, the sum of these two guys is equal to 0, which means basically that the actual regressor is grow rate, and the actual regressor is grow rate. Okay? But we reject it. Now, what is my mission today? My mission today is to explain you this. I don't want you to simply, you have to do like this. No, mechanically, no. You have to enter the theory. You have to understand what's going on here, okay? To do that, I move to the magic, to some magic stuff. So the magic of the F distribution, okay? So I'm going to bother you. I know that this is boring for you, but if you want to play guitar, if you want to become Jimmy Page. Do you know Jimmy Page? Because my son says that I'm a boomer in music, so Jimmy Page should be a very old man for you. But please believe me, he's a genius as a guitarist. You don't know Jimmy Page? Is there anyone who knows Jimmy Page? Oh, wonderful. Can you say who is Jimmy Page?
I think he was the guitarist for Led Zeppelin.
Oh, very well. Oh, let me show you. Let me take. I understand why my son is 13 says, Daddy, you belong to X generation, but you speak like a boomer. And you're right. He's right. Definitely right. Come on, Jimmy Page is. You should. Now, just don't look at long hair, blah blah. The important thing that this man was considered, say, the best rock guitarist, along with Jimmy. Can I say Jimi Hendrix? Is a name there? Okay. Okay, the three guys during the end of 60s, beginning of 70s were Jimi Hendrix, Jimmy Page, and who was the third one? Let's discuss that.
Jim Morrison.
No, come on, let's stop. We come back on econometrics. Okay, let's turn to econometrics. But if you have some pay, look at this. I recommend this. This is nice. Then I'll come back serious. Then I come back to serious stuff. But please, one day you go on YouTube and you write "blow up." Blow up is the title of a movie, very famous one. And okay. Okay, this is in this I will stop it in this. I recommend. I recommend to see this movie, Blow Up, and in this scene, which is a fantastic one, I would say, you will find two fantastic guitarists playing rock guitar. Okay, well, you can see that. You will get some fun. Let me come back to serious stuff.
Who is the third one?
The third one was Eric Clapton, was considered Eric Clapton. But in this movie, there is also Jeff Beck, who was, there was this, before the Led Zeppelin, there was this, the Yardbirds, where there are two major guitarists, Jimmy Page and Jeff Beck. And in this scene, in this movie, Jeff Beck is playing and he breaks the guitar because for some, okay, you have to look at it and then we'll discuss one day. Let me come back on the econometrics now. Now, okay, imagine that x1 is chi-square q1 degree of freedom and x2 chi-square with q2 degree of freedom, okay? And let me say that chi-square, one way to see the chi-square distribution with 1 degree of freedom, you simply take a normal 0, 1, you take the square, and you take chi-square, okay? Recall that we said yesterday chi-square, these are always positive variable, okay, because we are considered squares, okay? Now, if you take x1 chi-square q1 and x2 chi-square q2, and you define the random variable w given by the following ratio. Numerator, the two variables must be independent. So it means that any probability concerning x1 is independent, is not related to any probability regarding x2 and vice versa. Okay? Now, the random variable w given by the ratio between these two chi-square divided by q1 and the second one divided by q2, as a kind of magic, we get this F distribution, Q1, Q2. The F the density of the F is very similar to the density of the chi-square. Indeed, you have positive numerator, positive denominator. Let me notice that if you take an F, if the chi-square at the numerator, you have just Q1 equal to 1 degree of freedom. So we have this F1 Q2 given by this object. Okay. I want to show you that this distribution, not the F, is somehow related to the student T. I am bothering you in the last days with the last class with the student T. Why? Okay, take Q1 is equal to 1, and you know that this ratio will be F1 Q2. Okay. Now, if I take the square root of the left-hand side, I have to take the square root also on the right-hand side. So if I take this square root here, okay, the distribution will be the square root of an F1 Q2, okay? And finally, look at here. If you have the square root of a ratio, it means that you have the square root of numerator. And if you take the square root of chi-square 1, you come back to the normal 0, 1. And if you take the square root of the denominator, you have the square root of a chi-square q2 divided by q2. And yesterday, I've been bothering you yesterday, not 3 years ago, yesterday. We saw that this ratio was a student t with q2 degree of freedom. So a student t with q2 degree of freedom is equal to the square root of an f1 q2. So there is a link between f distribution with 1 degree of freedom and q2, okay? And also let me notice this, that if you have a usual f, okay, and if you the number of degree of freedom at the denominator, we'll see that in our case, q2 will depend on n, on the number of observations, okay? And so if you have a situation where n, you can send n to infinity, large sample, so basically, the f, when the number of degree of freedom in the denominator goes to infinity, collapses to what? Basically, come back to the definition. If q2 becomes very large, also this number becomes very large, and say this number will become 1, and you end up only with the, definition of this, and you end up with only with the numerator. So what I'm saying is that when you have, this is important that you have to keep it in mind. When you have, say, an f where the number of degree of freedom in the denominator can be approximated by infinity, you have the following, say, we have the following approximation. A chi-square q1 is equal to q1 times f q1 infinity. Why? Because I said this guy becomes 1 when q2 goes to infinity, so you end up with this expression here. Okay?
I'm sorry.
Yeah.
Maybe that's a stupid question, but q2 going towards 0 implies that our sample is large.
Yeah, q2 not go to 0, to infinity.
Sorry.
Yes, exact.
We are passing from a small to a larger.
Yeah, exact. So when we deal case 3, when we move to case 3, large sample, Gretel continue to give you an f. But you know, since you know this theory, since you know what I'm telling you, you will know that you can test, you can use a chi-square distribution. But in small sample, you have to stick to the f. And now it is what I'm going, yesterday we saw in small sample, we have student t. In large, yesterday we were testing single coefficients, and the theory was, at the end of the day, was small sample student t, large sample normal. But on top of the student t, we needed normality in the errors.
But this is always for the central limit theory, because
Exactly.
Exactly.
Today, we will consider case 1, case 2, case 3, but the argument will be exactly the same. The only complication will be that we have to know these things here, okay? Let me say also that why do Gretel or Stata or any package tends to report the F distribution and not the chi-square distribution? Actually, some packages also report chi-square. Because, say, in large samples, the F is a good approximation. This thing on the left-hand side is a good approximation of the chi-square Q1. That's why the F is important. And now, before going on, I can go to the slides, and then we'll come back on slide number 3. I will take 10 minutes before the break, okay? The first break. I still need... it is Jimmy Page's fault, okay? Now, I come back on the slides, and I think we have all the ingredients. You should have the ingredients, all the elements to understand what they're doing here, which is the last part of testing restriction. That is the most general case. So yesterday we have been treating the single coefficient test. Today we are moving to actually we are very close to ending the program, I mean to finishing. Not that far. Here I am. So theory, I put full screen. Theory of test for general linear hypothesis in the linear regression model. And okay, we know that any linear restriction on beta can be arranged like this. The null is capital R beta small r, and we know now the meaning of these objects. Please recall the important thing, just the trick you have, I mean, the way to understand things is that the number of rows of the big R matrix are the number corresponds to the number of restrictions we want to test. So Q is the number of rows of the big R matrix, okay? And again, we distinguish case 1, case 2, and case 3. Of course, you understand that case 1 is just for teaching purposes. Case 1 has no meaning, is completely useless from the point of view of empirical analysis. Why I'm doing that? Just because we are following a path, okay? Just because in order to play rock, first you have to do exercise with the guitar, okay? That was the case 1. N is small and sigma square is known. I will treat this case, then we have the break, okay? Okay, again, when we are dealing with small sample, you should have understood now that we need the price we need to pay, we have to pay is that we need assumptions on the distribution of the errors. And our assumption is normality. We assume that the errors conditioning on X is normal, okay? And we have seen that also yesterday. Under this assumption, also the OLS estimator will be normal. And I'm repeating the same story. There is nothing new now. And of course, we have been discussing the case where we know when the OLS estimator is centered on the true value. We saw when we're dealing with cross-section data, we have this result here. I mean, we know that the OLS estimator is also centered on the true value. So, under normality and cross-section data, I can say that the beta estimator minus true value, conditioning on X, is normal, centered on 0, and with the following variance covariance matrix, which is the one from where we take standard errors, blah, 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 blah. Okay? Now, I want to, before stopping, yesterday we have been talking about property 0. Property 0 was, if you have a multivariate normal, any element of the vector will be normal. Now we are moving to property 1, which is very, if you know these properties, now you are going to see Professor Fanelli showing up nasty formulas. It's in there, we have hundreds of formulas, there are many, many formulas. I don't want you to know the formulas. I just want to know the property. Then you derive formulas by hand, as I do. Probably there are mistakes in the formulas, but not in the properties. So property number 1 says like this. Imagine that V is a multivariate normal, 0 expectation, and variance covariance matrix capital V, okay? You know, capital V, it will be P by P. On the main diagonal, we have variances. What do we have on of diagonal terms. Covariances, and then from covariances, by combining covariances with variances, we obtain correlations, okay? But the off-diagonal terms are covariances. Now, if you take a matrix A, okay, not random, so like our big R matrix, you have just imagine that your A contains zeros and 1, okay? With Q rows and P columns, please, P is just the dimension of V. And now let me consider this object here. This is a linear combination of the element of the V vector. Okay? Then property number 1 says that this guy here is still multivariate normal. What is the expected value of this guy? Will be again 0, but it's not at 0 p by 1, at 0 q, because this vector here now is q by 1. Okay? What about the variance covariance matrix of this guy? I'm going to apply the sandwich rule. I've been talking about the sandwich rule several times. So, very well. The variance covariance matrix will be A, V, A prime. And I stop here now, and when we'll start at I should say 420, because then we'll make a break. So we make a short break. We start at 420, and I will start exactly from here, okay? But property 1, I'm giving you the properties you need to know, okay? So we make a break. Don't go too far in the, just we'll start at 420, okay? Okay, guys, I start. Okay, guys, let's start again. So what you're doing now is is it possible to close the door, please? It's possible to close it. Thank you. Thank you. Now, this is my starting point. And you will see today, what we are doing today is deriving a world test. In one of our classes, I'll show you who world was, okay? Now, you will realize that if you know the properties I'm giving you, the properties must be, you have to know the properties, not the formulas, but if you know the properties, you will be able to derive a world type test yourself. So no nasty formulas, just we apply rules, properties. So this is the properties of the OLS estimator under normality of the error term, okay? Imagine that we are dealing with cross-section data, so we know that beta 0, the estimator is centered on the true value, beta 0. This will be the expected value, okay? Now, think about what is the beta. This is the estimator of beta coefficient without any restrictions, okay? And what is the big R matrix? Is the matrix by which we deals with the restrictions, okay? Now, if you apply, this is my starting point, and if I apply property number 1, you should realize that if I multiply on the left-hand side by the big R matrix, here I have normality, I still have normality. The only difference will be in proposition 1, in property 1, I have basically the sandwich rule in the variance square matrix, and you can see that I have the sandwich rule exactly in the variance square matrix. So the big R matrix is going to play, okay? So if I pre-multiply capital R by beta hat, I get this number. If I pre-multiply capital R by true value, I get this number. So we have this result. And I simply apply, this was my starting point, implied by normality of the error term, and by applying property 1, I am here. So nothing very mysterious here. Now, second step. Under the null hypothesis, please recall that this R beta 0 under the null is small r. Please, just come back on the null. The null was this one. So when we evaluate beta to the true value beta 0, we get on the right-hand side small r. And this is what I have done here. So I have this result. I have that under the null hypothesis. What is the interpretation of this result? Under the null hypothesis, this is a linear combination of the OLS estimator. The linear combination of the OLS estimator is normal, 0, with the following variance square matrix. Okay? And there is nothing very difficult to know or to understand up to this point. We only have to study. the properties. Now, we know property 0, property 1. I'm going to give you property number 2. Property number 2 says, and property number 2 relates the normal to the chi-square distribution. If you remember, look at this. I already give you the link between the two in a very simple way. If I come back on my to the mysterious stuff, recall that I already give you this result. I said if z is normal 0, 1, the square of z is chi-square 1. Now I'm going to generalize that, okay? And that is property number 2. Property number 2 will be a simple generalization of that. Property 2 says, okay, if V is a multivariate normal, 0, big V, okay, then if you take this object here, this is a scalar. The variable you have on the left-hand side is a scalar because this is V prime is a row times a matrix times a column. And you can check that this is just a scalar, 1 by 1 element. This scalar is distributed like chi-square P. Please recall that P is the dimension of V. So in my previous example, in the one I'll show you before, P was 1 because I had only one random variable. Big V was equal to 1. And this number was simply V squared. V squared will be chi-square 1. Since I'm not saying strange thing. I'm coming back to this. Okay? So we are simply property 2 generalized things that we already have seen. Okay? Now, what is the use I'm going to do of property number 2? You understand that I have, now, this is my V now. Imagine that this is my V. This is my big V. I can define, if you agree with me, I define the following test statistic that I call W. I call it W just in honor of Wald, who was we already have been talking about him. Okay. What I'm doing, this look awful. Oh, this is incredible awful. No, it is not. I'm simply applying property number 2, where my V is this number here. My V is this thing. My big V is this object here. So what I'm doing is simply applying property number 2. And by applying that, I have that this W, defined like this, will be distributed under the null as a chi-square with Q degree of freedom. And I don't remember this formula. I just remember property number 2. Okay? Now, imagine that I'm considering under the fake hypothesis that we know sigma square epsilon, okay? So if we know sigma square epsilon, this is a test statistic because I can calculate this object here because beta hat, it is the column of beta estimator I get from Gretel. I know big R, I know small r. This is something that can be computed by my software, my package. Also inverting this is a job for my package. So I have a number here. And I know that the realization of this number is generated from a chi-square with Q degree of freedom. So the test would be reject the null hypothesis if you compute this number. If this number is larger than the critical value taken from the chi-square distribution Q degree of freedom, you reject it. And during the 90s, I had to go to I had to look for the table of the chi-square distribution with the Q. For instance, in our exercise, I had to look for the chi-square with 2 degree of freedom, and I take the critical value from the table of a chi-square with 2 degree of freedom. Today, we don't need that because the p-value, the way to go with the p-value is that we reject the null if the p-value of the test is less than alpha. Okay? Remember that the p-value of the test is the probability that a chi-square Q distribution is larger than the computed value of the test statistic. Okay? Case 2, of course, case 1 is meaningless in the sense that we don't know sigma square. So we have to replace it with sigma square f. Okay? Now, I could present the thing like, okay, let me address case 2. Again, we need normality for the error term because small sample. And we know that in this case, under normality, the OLS estimator, we still have this result here. Okay? Now, as in case number 1, if I apply property 1 and property 2, we define this W like this, and we know that under the null, it is chi-square Q. Okay? I'm just repeating what you already said, but the question now, is Wn a test statistic? The answer is not, because not yet, because we don't know sigma square epsilon. So a very natural thing to do is to replace sigma square epsilon with with the estimator. Okay, and we know very well this estimator. Now the story, the narrative is once we replace sigma square epsilon with its estimator, this W will be no longer chi-square distributed, but for some magic we have the F. And let's come back to the magic. Let me see what the slides say now. But this is the let me come back on the magic on the slide on the F distribution, and I go on number 3. Okay. Okay. Oh, sorry, where is it? If you have any question at home, please let me know. Okay. Okay. Small sample, please recall that we are testing the following null hypothesis. Okay. We have normality. Just repeating things that I'm repeating things several times because that is the way that you learn things. Okay. You learn following me. So under this assumption, we know that Wn is chi-square Q. Okay. And now I want to come back on yesterday result. Yesterday I said, oh guys, and I had a question from Salvatore on this result. If the ratio between the estimator of sigma square epsilon and the true sigma square is distributed like a chi-square n minus k degree of freedom divided by n minus k. This is yesterday result. Okay? At least on my comeback on yesterday notes, comeback on yesterday registration, you will find out. Now, let me define this W star. Simply, I'm dividing Wn, so we have this Wn. I divide this Wn by Q. Please recall that Q is the number of restrictions we are considering, okay? And I divide by this ratio here, okay? And now what I'm going to show you is that we have, in the numerator, we have a chi-square distribution with Q degree of freedom divided by Q. And in the denominator, we have chi-square n minus k divided by n minus k. Indeed. This W star, if you do rewrite it with the algebra, okay, is given, the numerator is given by this object here, okay? I'm noting any magic. I simply have this Wn that we know very well divided by Q, and it is this object here. And we know that this is a chi-square Q distributed divided by Q. So the numerator is as the following distribution. What about the denominator? We already said it. It is chi-square n minus k divided by n minus k. So Our theory today says that the ratio of two it is possible to prove that they are independent. We skip that proof because it does not make sense for us. But we should prove that the two random variables are independent, okay? But we can skip that. So this ratio, this W star, is distributed under the null like an F, Q, n minus k degree of freedom. The only difference is that, okay, yeah, this object is distributed like F, Q, n minus k, okay? Under, of course, the null hypothesis. Now, you understand that case 3 will be, okay, I come back on the slides, then we also come back on the empirical exercise. But is it clear, guys, up to this point? Yeah, thank you. I can come back on the slides. And so, this is the result on the slide, okay? Again, we have that under the null, our test statistic, which is in the written by hand slide, it was W star. It is written like this in the slide, but under the null, we have an F, Q, n minus k. And so, again, we have a test statistic. We know the distribution of the test statistic under the null. Again, we reject the null if the computed test statistic, I should have put star here, okay? This is a W star n, okay? Define. If the computed test statistic is larger than the critical value taken no longer for the chi-square table, but from the F table. So during the 90s, I had to look for the table. In the 90s, I needed a table for not for the normal, because more or less we know that with the normal you have -2 + 2, and you are done. Student T, well, you need a table. For the student T, you need a table for chi-square, you need a table for the F distribution. So, if you like to reject the null by using critical value, you have to look for the critical value from a table of a F, Q, n minus k. But again, any package will give us the p-value. So we reject the null if the p-value associated with the test is less or equal to alpha, where we prefix alpha. Again, the p-value is the probability that the F, Q, n minus k is larger than the computed value of the test statistic. Last case, case 3, n is large and we don't know sigma square epsilon. Now, again, what we do now, we appeal to the large sample property of the OLS estimator. We don't need normality of the epsilon here, because there are some central limit theorems, as Salvatore was pointing out before, because of some results of math of probability, okay? We have that the beta estimator is if n is large enough, is normal, centered on the true value. The estimator is consistent, although in this case, with the following variance square metric. So in this case, we don't have to pay the price of normality. We have normality just because of the large sample. We don't need the epsilon to be normal, okay? So whatever the distribution of the variable, we have that the OLS estimator is like this. And now, again, since also the estimator, I mean, what we can do, since the estimator of sigma square epsilon is also consistent for sigma square epsilon, I can replace this sigma square epsilon with its estimate. And again, I still say that estimator minus true value for large n is normal, centered on 0, with the following variance square matrix, where I know everything. You understand that when you have a normal and you know that the normal is centered at 0 and you know the variance, you have everything. You are done. Indeed, now if I apply property 1 and 2, exactly as I did before, I define this Wn this W test statistic, which is given by this expression here. This is the same as, you remember, it is the same as when sigma square was known. But now what I've done, I have simply replaced sigma square epsilon with its estimator. But this is under the null. This is going to be chi-square with q degree of freedom because of property 1 and 2. So again, we reject the null, and this is our case in the consumption, in the gasoline, in the model consumption for gasoline. It is exactly our setup where I said that we can approximate. In that case, actually, we have 35 observations, which is not very large. But I said, let's assume that 35 is large, okay? It's infinite. So again, what we do, we reject the null if our Wn is larger. And I want to come back on I will come back on Gretel now, okay? Because you might say, well, I want to just pose your attention on one point. So again, if the computed test statistic is larger than the critical value, now we come back on the chi-square distribution. I need, during the 90s, the table of the chi-square. And the alternative is the p-value. Okay, so I want to come back on the exercise, the empirical exercise, and in particular, the test was. Oh, okay. Look at here now. Gretel, of course, this was the test we did for our restrictions, and you can see we reject that given the p-value. But now the question might be, what? I mean, if Gretel doesn't large sample or small sample, Gretel just follow commands, inputs, lines, code. So it's very convenient for Gretel. We know that, I mean, if 29 is large, we know that an f, the number of degree of freedom in the denominator is large, we can say that we have a link between the f and a chi-square with 2 degree of freedom. So basically, the f is a smart way to go, regardless of whether we are in a small sample or large sample. But there is one important point that we have to know. The researcher has to know that if we are in a small sample, in order to use the f, we know that we need on top normality of the error term. If we are dealing with a large sample, I don't care about normality of the error term. Okay? And unfortunately, it was very nice. I mean, it was very intuitive that the coefficients were very close to some 0, but we reject that now. Okay? Any question, guys? Clarification? You look perplexed, no? Now, going on with the slides, we have to finish with confidence intervals and prediction forecast. But if you have understood testing hypothesis, this will be very, very easygoing. Okay. And this is written by hand. Okay. So let me give you an example. So imagine that we are in the classic linear regression model. There is a model, okay? Now I'm using notation with the index I, okay? Now we know how to test the linear hypothesis on the coefficient beta, okay? Please recall that we, regardless of whether we are testing single coefficients or linear combination of coefficients, we have to distinguish in our mind think about this case 1, case 2, and case 3. Case 1 is just the important one are case 2 and case 3. Okay. Now, imagine that we estimate our model and we are happy about our model. One thing we might like to do is building confidence interval for, say, single coefficients in beta. Let me check whether Gretel does it, if it does, and how it does it. So, confidence interval for coefficients, okay? After we estimate a model, let's see, I want to show you things in Gretel, and then we motivate, we see what's going on in Gretel, okay? So I want to compute confidence interval for coefficients, and what Gretel does is the following job. Say, this is the estimated constant, and it says the 95 confidence interval is given by this range. This is the estimated coefficient associated with the income. This is the point estimate, and this is the confidence interval around this point estimate. We are going to rationalize what it is, okay? But some packages, for instance, if I remember correctly, Stata immediately give you the confidence interval in the estimation output. You don't need to ask for confidence interval, but I like much more Gretel because, well, it depends on what you want to ask to your data, okay? But, okay, I want to rationalize now this number here, but it will be very easy now. Indeed. So, example, this is our model for consumption at time t, disposable income at time t, consumption t minus 1 plus error term, okay? Imagine that we are interested in building a beta 2 coefficient. In this case is the elasticity of consumption with respect to income, okay? It is an important parameter, and of course we are interested in building, to estimate this parameter and to build a confidence interval for this parameter here. And again, now let's distinguish between, I'm following now always the same argument. Case 1, small sample. Case 2, large sample. So if you are dealing with a small sample, n is small, we know that in that case we need normality of the error term, okay? And under this assumption of normality, we know that the OLS estimator is normal, okay? Then, from property 0, we know that any element of the beta vector will be normal, but this is a multivariate, this is a scalar normal, okay? Again, what is C22? This is our class yesterday. C22 is the second element of the diagonal of x prime x inverse. If you take the square root of this number, you get the standard error of beta 2, okay? We said several times. And we know, since we are a small sample, that if we the random variable given by, say, beta 2 minus true value, or beta 2 divided by standard error, it is a small sample. Recall that. This is yesterday's class, okay? N is small. So this ratio here, the T ratio, this is the T ratio, is student T with n minus k degree of freedom. This is yesterday class, okay? Now, given this information, we know everything. We have everything in our hands, because I know that the probability that the random variable W is between Q1 minus alpha minus Q1 minus alpha, where what is this Q1 minus alpha? Is the 1 minus alpha percentile from the student T distribution. We know basically that the probability that the student T is, say, between minus 2 point something plus 2 point something will be equal to 90%, for instance. You prefix the alpha exactly as you do when running tests. So given this, if you know that W is student T, you can take, this statement, and now you solve it basically what I do, I replace this W with this expression here, the one I'm touching with my hand, okay? And you do some computation, and at the end of the day, you realize that the probability that the true unknown value, you don't know this number, you don't know the true value. You have the OLS estimate, you know that the OLS estimate minus true value divided by standard error is student t n minus k in small samples, okay? So you rearrange a little bit, say, this expression, at the end of the day, you realize that the probability that the true unknown value is between, now, estimate plus something, estimate minus something, will be 1 minus alpha. So what are these objects here? This is the upper bound of the confidence interval, and this is the lower bound of the confidence interval. The upper bound involves, say, the point estimate of beta 2 plus estimate of variance or sigma epsilon, standard error, and the quantile or percentile from the student t distribution. That's it. So the number you find, okay, I go on. In other words, the 1 minus alpha % confidence interval for the parameter beta 2 is given by point estimate, point or less estimate, plus minus standard error times quantile. How do we interpret this confidence interval? The probability that in repeated samples, the interval, this object here, contains the true value of the coefficient that we don't know is 1 minus alpha. The statement is this one. The probability that the random variable, as you can see, is not this beta 0. This is a true value that we don't know. The random variable is here and here. So the probability that my intervals, if you do in repeated samples, will contain the true value will be 95%. Imagine that you do 100 samples of your data, if you can do that. Basically, 95 times out of 100, you will find that the true value is inside the confidence interval. So, coming back to the example, so basically, 95, if the object of interest is given by this number, okay, this parameter, okay, with 90% confidence, 95% of times, this interval will contain the true unknown value. And how do we build this lower bound and this upper bound? It's given by the point estimate of the parameter. So let me think about this lower interval. It will be the point estimate minus standard error, the estimated standard error times the quantile from the distribution. In this case, in this example, we have a large sample distribution, so the quantile will be taken from which distribution? Normal, exact. So the quantile, if you're building 95%, will be 1.96. And what about the upper interval? The upper bound will be the point estimate plus standard error times 1.96, and you get this number. Very, very easy.
Sorry,
yeah.
You're saying that it's confidence interval. You're saying that if the percentage that our true value is that in that confidence, if we run multiple samples, but it's true also for one sample.
Yeah. You never. I mean, it's just a logical experiment. If you could resample, of course, you only just one sample.
It's still true.
Yeah. But the point is that my point is that this probability statement regards not that. I mean, regard the bounds of those are random. These are random variable. These are random variable. This is the true value which is inside. So the probability that the intervals will contain the true value is equal 1 minus alpha. Okay. And so the typical interpretation is that imagine that you could repeat sample several times, you will find that 95% of times out of 100, you will find that true value is inside that confidence interval, the interval. Okay. Of course, if we are in the large sample case, everything is exactly as before, but the only difference will be that we take the quantile from the normal, not from the student t. That's it. And prediction, we can skip prediction for today. What I'll do now, so since we can finish a little bit, I want to finish today at 45, so we can take now another 15 minutes break. So it's we'll start again at 5:10, okay, and then we go up to 5:45, okay. So we make a break, and I'm quite happy about the. Okay, we are. We can. We said that we're starting at. Let me check what I wrote. Okay, so I have to start. Okay, I'm quite happy to claim that, say, basically we have been covering. I'm moving to section number 7 on our slides, and entitled misspecification issues. Basically, but we are already have been thinking about, say, misspecification issues in the sense that we have been discussing how to evaluate, how to claim that a model is good or not once we estimate the model. So today I want to start discussing that, and let me say that the final part will be moving regressors to we are seeing that it's an assumption that no does not always is not always valid in empirical research. So we'll discuss how to face this situation, and we'll see a novel estimator, the estimator. Today, I want to spend a few words, and also next Friday, about, say, evaluating whether a model is good or not. So, I go there to the slides, so I have misspecification issues, and we'll come back on our example of model. Let me start exactly from that example. The baseline model was for consumption of gasoline. Please recall that CT was the log of real per capita gasoline consumption, PT was the log of price of gasoline, YD was the log of real per capita income. Error term. In a sense, we have a model, we explain gasoline consumption with prices, with income, with gasoline consumption in the previous period. The error term should be what is left about gasoline consumption once we include once we account for all the information, all the theory, all the data we know about, all the knowledge we know about gasoline consumption. So the error term should be something unpredictable, something there should be no signal in the error term. So, and I want to give you the intuition which are the consequences of, for instance, of not having an error term which is uncorrelated over time. Okay, so that's why one of the first checks I do when I estimate a model like this is testing homoscedasticity. But okay, but we know that if we don't have homoscedasticity, we can go for robust standard errors. We know that in that case we don't have the best standard errors ever, but anyway, we can make inference by using robust standard error. But now I want to pose your attention on the other problem, the problem when epsilon t is correlated. So the case where the big sigma matrix in the matrix notation is not diagonal. So we have some non-zero diagonal term. Okay, and so I want to discuss in particular with you. For instance, assume that the error term in our model epsilon t is generated by the following model. The following model is not. You will discuss this model with Professor Panagonitis more seriously. But look at this model. So in this model, the error term at time t is given by a coefficient ρ1, where ρ1 is between 1 and -1, times epsilon t minus 1 plus Vt, where Vt is a white noise term. So what do we need by white noise? Vt means white noise means that Vt has 0 expectations, has constant variance sigma square V, so it is almost stochastic, and it means that Vt is uncorrelated. Vt, not epsilon t, okay? So in this model, epsilon t is related to epsilon in the previous period. And it is possible to prove, I skip a mathematical derivation, but it's possible to prove that the covariance between epsilon time t and epsilon time t minus s, where s can be 1, 2, 3, blah, blah, is given by a power s of rho 1. So what I'm telling you is that the big sigma matrix, in this example, if the error term is generated like this, the big sigma has powers of rho 1 in the off-diagonal terms. Think about, say, the matrix representation of this. Think about the metric representation of this model. In particular, think about, say, the big sigma matrix in this setup. If epsilon t is generated by this model, you will realize that the big sigma will be no longer diagonal because of this condition. Okay? The question is, can we claim that in this case, regressors and the error term in this particular example are uncorrelated? We know that absence of correlation between regressors and error term is a crucial condition for the OLS estimator to be consistent. And we know that we need consistency under the interpretation that causality runs from the regressors to the dependent variable. Okay, so now I want to give you the intuition why. So you will understand if you, I mean, you can understand why I were concerned yesterday's model. No. This one. I was very concerned about, this model. I estimated this model. It seems that coefficients more or less reasonable from an economic point of view, and unfortunately, I rejected the null hypothesis that, say, I had the growth rate